here we go. 11.1, we're splitting it into two, just starting slow today. We're not going to do all of 11.1. So 11.1a is all about space figures. And just another word for space figures is 3D figures. What's a three-dimensional figure? It has width, height, and depth. Yes, it has length, width, height, yeah, however you want to word the three. But this way, this way, this way. What?
How have we never learned a space figure? That sounds a lot cooler.
I know, right? I don't know. So the term that we're going to use here is polyhedron. And a polyhedron is just a space figure, so a three-dimensional figure. With, this app updated it, and it just does not like me anymore. A three-dimensional figure, we'll do this. Three-dimensional figure whose surfaces are polygons. What's a polygon? Give me an example of a polygon. Maybe that will help. What? A hexagon, a square, a rectangle, a triangle. Not a circle, right? Circles are not polygons. So polyhedrons are three-dimensional figures whose surfaces are polygons. There's a few different things you need to know about a polyhedron that we're going to use today for this guy called Leonhard Euler. Anyone heard of Euler's formula? Maybe not. But Leonhard Euler was a brilliant mathematician. He was Swiss. And he came up with a couple formulas that we're going to use today that just hold true for all polyhedrons, okay? So we're going to start with this. If you are capable and willing and taking notes, you can draw for yourself a box, a rectangular prism, if you will. The way I always draw it is I draw that front rectangle, and then I draw the angles off from it, and then I just connect them in the back, and then draw your dotted line in. You are welcome to draw two rectangles and then connect those two rectangles, but I like the dotted lines, so that's why I don't. Okay, so this would be a polyhedron. On this polyhedron, we are going to find three different things. We're going to find vertices, we're going to find faces, and we're going to find edges. So we're going to start with the vertices. A vertex is where three or more, actually I lied, we're not. We're going to start with faces. Take it back. Faces are these. This would be one face of your polyhedron. Basically, a face is just any of the polygons that you see there. So in this case, it's a rectangle, but we call it a face of the figure. So on that figure, how many faces do you see? 6 faces, okay? Second thing we're going to point out are the edges. And this line right here would be called an edge. And an edge is just where two faces meet. How's that color? Kind of hard to see. So that's an edge. Okay, and then the third thing, let's see, we're going to change this yellow. To a purple. Third thing is vertices. So singular, this is a vertex. But if you pluralize it, it's vertices, right? And that's where 3 or more edges meet. Okay. So how many vertices do you see in this picture? There's 8, right? 1, 2, 3, 4 up on top. 1, 2, 3, 4 on bottom. So there's 8 vertices. How many edges are there? not 10. There's 12, right? There's 1, 2, 3, 4 on bottom. There's 1, 2, 3, 4 on top, and then the 4 that connect those, 1, 2, 3, and 4. Okay, so 12 edges on that, 6 faces, 8 vertices. Okay? Okay, so let me give you another picture, and you can kind of lay it out for me. First example here. Let's say we have this picture. Okay, first of all, we would call this a triangular pyramid because the base is a triangle. It makes a pyramid shape. So this is R, S, T, and U. Okay, I want to know how many faces, how many edges, and how many vertices are there. And just so you're clear on how I typically do this, I usually just give it a letter. Actually, let's change color so you can see. Oops. Okay, so we'll call our V our vertices. E is our edges. And what did I use for our faces? Red. And F is our faces. Okay, so how many vertices do you see in this picture? There's 4, right? There's R, S, T, and U. So there's 4 vertices. How many edges do you see? What? There's 6, because the dotted line is actually an edge. It's the only reason it's dotted is because it's hidden, right? So that's just showing us that we can't actually see it right now, but it is there. So there would be 6 edges. And then how many faces? 4 faces. There's the base, the bottom triangle, and then there's 3 triangles that wrap around, okay? So your faces would be 4. So it goes 4, 6, 4 on that one, okay? So here's where Euler comes into play. And his name doesn't look like Euler, but you say it Euler. It looks like Euler. Not Bueller, Euler. But it's Euler, okay? Euler's formula. What he figured out is that there's a relationship in polyhedrons, vertices, faces, and edges, okay? And the relationship he found is this. Euler's formula says if you take the faces and add the vertices, it will equal the number of edges plus 2. Okay, so that 2 is always there. Faces, vertices, and edges can change, but the 2 stays the same, okay? So if you look at the one we just did, faces plus vertices should equal edges plus 2, right? So 4 plus 4 should equal 6 plus 2, and it does. Okay, so there's always that relationship there. The main reason we do this is as a check, just to see, like, does it hold true with Euler's formula? We don't do a ton with Euler's formula, but it's kind of the intro to what we're doing. So we are going to do one more of these and check it with Euler's formula. And bear with me, because my drawing of this one is always a little bit off, but we'll get the point across at least. So we're making kind of a square, maybe rectangular pyramid, and then below it, the same thing. So it's kind of a pyramid with a pyramid, put the 2 bases together, there's your figure, okay? So if this is my figure, we're gonna do faces, vertices, and edges in this picture. How many faces do you see? And these are just faces that, like if this were an actual figure, faces that are touching the outside air, okay? There'd be 8, right? 9 is tempting because you have the one in the middle, but that one's not exposed to the outside, okay? So don't count that one, but there would be 8 faces. There's 4 triangles on top, there's 4 triangles on bottom, so 8 faces. How many vertices do you see? How many? 6. You have 1, 2, 3, 4, 5, and 6. So there's 6 vertices. How many edges? There's 12. Okay, now here's the deal. Could you figure out the edges without looking at the picture right now?
Yeah.
You could plug it into Euler's formula, right? So it goes either way. You can either not have to count it and use Euler's formula to find it, or you can count them all and double check it with Euler's formula. They both work, okay? But if you count them, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So there are 12 edges. So let's check it against Euler's formula. It should be faces plus vertices equals edges plus 2. Does that equal each other? 14, right? 14 equals 14. So it does check out with Euler's formula. Questions on that? Okay, so that's kind of the main concept of what we're doing today, but they made an alteration to Euler's formula when they took it into account with 2-dimensional figures. So this is Euler's formula for 3D figures, okay? Oops, I'm just gonna write that up here. If you're taking notes, maybe just write 3D behind that one, because it is the main formula that Euler came up with, but then they did find this other one as well. So for 3-dimensional figures, f plus v equals e plus 2. But if we do 2-dimensional figures, Euler's formula, I should not use that color, huh? It's not the greatest. So for a 2-dimensional figure, Euler's formula says this: f plus v equals e plus 1 instead. Okay, so basically what they're doing is they're taking the 3-dimensional figure and they're making a net out of it. Remember chapter 1, lesson 1, we learned about nets, where you took the figure, I used a diaper box and I laid it all out. You remember that? Those of you that had me first semester. So lay out a figure. For instance, if we laid out a cube, okay? In a cube, your squares, I'm going to be one short. That's not beautiful. Sorry. Use your imagination. Okay, so this would be the net for a cube, right? We want to figure out faces, vertices, edges. What do we have? Does it work out? So how many faces do you see for this? There's 6 faces, right? 1, 2, 3, 4, 5, 6. Okay, so 6 faces. Actually, let's just do vertices next. How many vertices? And I would say it's helpful to just mark these as you go so you don't double count anything or you don't miss anything. So maybe mark it as you go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, 14 vertices. And then the last one, edges. So again, I would mark them as you go just so you're good. If you're not drawing them, then I guess you don't mark them. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so now look at Euler's formula. It's f plus v equals e plus what for 2-dimensional? Plus 1, right? So you're going to go, does that make sense? 6 plus 14 equals 19 plus 1. This Euler guy was pretty intelligent because he figured it out. It does make sense. So 20 equals 20, and that works out. Okay? Faces, edges, and vertices. That's really all we're doing today. Keeping it simple here. And you have 20 minutes still, so you can probably get your homework done in that time because it's not super long. Leave it up there? Yeah.